Hello, my name is Rauhaus, and this is my third organic chemistry lab report in the video format. Today for this lab report, I will be demonstrating the difference between a washing and extraction technique. I will be demonstrating a procedure on how to separate a solid mixture of caprolactone, acetic acid, and benzoic acid. I will be giving an analysis of the organic synthesis online lab, and I will be giving a summary of all the purification and characterization techniques taught in this lab class. Often in a laboratory setting, you are given a solid mass with two compounds and required to separate them. There are two techniques you can use. One is washing and one is extraction. These techniques are very similar and both involve first dissolving the solid in a solution. That solution is then added to a separatory funnel, and a second solution, which is immiscible with the first, is added. By carefully choosing the solution, and by possibly washing with an acid or a base, we can manipulate the solubility of the solids within the two solutions and end up with two separated layers in the separatory funnel, one dissolving one compound and the other dissolving the other compound. And depending on the solution of interest, we can either consider this a washing or an extraction. So for my demonstration today, I will be using ice and Orbis as my two solids that we need to separate. First, you can see I'm putting them in the apparatus, and then the next step in my procedure is to dissolve them in a solvent. The solvent I'm using today is oil. So the first step is to dissolve it in the oil, as you can see there by my mixing. And the second step in the procedure is to add the second solution. My second solution is water, as water and oil are immiscible. So you can see immediately that the water is pooling at the bottom and the oil is at the top. And by mixing the two layers, you can see that the ice is collecting at the top with the oil and the Orbis are at the bottom with the water. So we consider this an extraction if we want to keep the ice and a washing if we want to keep the Orbis. So obviously there are very many techniques on how to separate two solids from each other. These are just two of them. But as you progress in your career as a chemist, you will be using these in your labs. To quickly summarize, washing is a technique where you dissolve impurities out of a solution to leave the compound of interest. And extraction is dissolving the compound of interest in a separate solvent to be able to take it out of an impure solution. So for question number 2, I have been given unknown mixture number 3, which is a mixture of benzoic acid, acetic acid, and caprolactone, all in a crude solid mixture. And over the next few clips, we will demonstrate on how to separate these three solids into their individual components. So some limitations that we have in the organic chemistry lab is distilling solutions with boiling points over 110 degrees Celsius. So for my procedure today, I will be mostly working off of some of the techniques that I mentioned in question 1 and working with different solubilities and precipitation of certain solids. So to begin with step 1, we will be dissolving acetic acid and caprolactone in cold water and expecting the benzoic acid to precipitate. The first step in my procedure is to take a beaker of water and place it in an ice bath to cool down the water as much as possible. We do this step because the colder the water, the lower the solubility of benzoic acid is in solution. So the point of this step is to get the water as cold as possible so that the benzoic acid dissolves as little in solution as possible. So this step is dissolving all of our solids into the water. And by doing this, we will get benzoic acid precipitate and caprolactone and acetic acid dissolved into the solution. So step 1 of my procedure in separating these compounds works very heavily on the lack of polarity of benzoic acid. Even though it does have that carboxylic acid functional group, the benzene ring plays a large role in reducing the polarity of the molecule, allowing it to precipitate out when dissolved or attempted to dissolve in water. The polarity of acetic acid and caprolactone allow it to be dissolved in solution and therefore separate those two compounds from the benzoic acid. The next step of my procedure is to pass the solution through a gravity filter, which allows us to keep the benzoic acid in the filter and allow the acetic acid and caprolactone to pass through the filter and be collected in the solution in the Erlenmeyer flask. As you can see here, I have a demonstration of a gravity filtration. So as we pour the solution through the filter, the caprolactone and the acetic acid will pass through the filter into the solution at the bottom of the Erlenmeyer flask, and the benzoic acid will be held in the filter at the top. So we can take the benzoic acid from the filter by folding it and pressing all the water out of it, and then it can be taken as a precipitate solid at the end of our procedure. The third step in my procedure is to separate the caprolactone and the acetic acid from each other. To do this, I'm going to mix in an organic solvent of hexane and place them both in a separatory funnel and do an extraction technique like I outlined in question 1. So hexane is a long alkyne and therefore very non-polar, and it works very well towards the caprolactone because the acetic acid is very polar and dissolves very well in water. This plays very well to the degrees of polarity, meaning that the acetic acid will stay dissolved in the water, and with the addition of the hexane, the caprolactone will be drawn to that solution and is very undersaturated, and the solute will be drawn to the undersaturated solvent, and we will end up in two immiscible layers, one of the hexane containing the caprolactone and the water containing the acetic acid. So here we have our aqueous acetic acid and caprolactone solution taken from step 2 in the gravity filtration. Once it's in the separatory funnel, we will add a layer of hexane, which is again an organic solvent, and we will plug the separatory funnel and mix. With this mixing, the caprolactone will be dissolved by the hexane as it is soluble in most organic solvents. And we will also wash with a bit of NaOH to be able to deprotonate the acid and make a aqueous acidic solution. Once these two layers are separated fully, we can mix a few more times, gas the separatory funnel, mix, make sure that all the caprolactone is dissolved by the hexane, and then we will drain off the lower aqueous acetic acid solution into a beaker, and then we will drain off the hexane into a separate beaker, and then we will have our 3 different solids in 3 separate containers. The purpose of washing with NaOH in the separatory funnel is to, 1, deprotonate the acetic acid to allow as much of an ionic connection in water as possible so that it dissolves very well, and also to add ions to the water to saturate it more, causing as much caprolactane as possible to be pushed out of the water and dissolved into the unsaturated hexane. After our separatory funnel technique, we will drain the lower layer of acetic acid dissolved in H2O into one beaker and the top layer of caprolactone dissolved in hexane into another beaker. So after that step, we will have our benzoic acid separated in its precipitate form in a filter. We will have acetic acid in one beaker and caprolactone in the next. Now, I will be reviewing the Organic Synthesis Online Lab. For the Organic Synthesis Online Lab, we will be doing a substitution reaction of 2-naphthol and using the solvent NaOH and ethanol, and the substrate iodobutane will be synthesizing 2-butoxy-naphthalene. The first step in the procedure of the Organic Synthesis Online Lab is to, in a reaction flask, add 3 pellets of NaOH, add 0.5 grams of 2-naphthol, and 5 milliliters of 95% ethanol. You will then attach a condenser to the top of the reaction flask and set up a reflux apparatus. You will put it on a hot plate, and boil until all the solids are dissolved. Once all of your NaOH pellets have dissolved, you will then take off the reflux apparatus and add 0.5 milliliters of 1-iodobutane. You will then attach the condenser back to the top of the reaction flask and boil for 1 to 1.5 hours. This is the first time in the Organic Synthesis Lab that we encounter digital pipette. These give very accurate volume measurements and are a great tool for chemists. It is important when after you insert the tip into the 1-iodobutane that you do not then place the digital pipette on its side, as the liquid will contaminate the sensor inside the pipette. So once you use the tip to dispense your 0.5 milliliters of 1-iodobutane into your reaction flask, you will then remove the tip and then you can lay it sideways on the desk. After boiling for a further 1 to 1.5 hours, you will then take the reaction flask and do a TLC plate with the mixture inside. You do need a standard though, and the standard that I'm choosing for this experiment is 2-naphthol. I'm using 2-naphthol because it's a good standard to see if the substitution did actually happen, and it could be a good benchmark to compare your product. To do your TLC experiment, you will first need to take a double-ended capillary tube and heat it over an ethanol burner. Once the tube gets hot and starts to melt, you will then pull it apart to make 2 separate capillary tubes. For your TLC experiment, you will take 1 microcapillary, put it in the reaction flask, and then dip dots onto A and the combined spots. You will take the other microcapillary and dip it into the 2-naphthol dissolved in 95% ethanol, and dip it onto the combined spot and also the B spot. After you're done with the TLC portion of the experiment, you'll move on to what's called a workup. Workup is isolating and purifying your solid, which is in solution. In this experiment, we will be pouring the reaction flask over 10 grams of ice and allowing our solid to precipitate out of solution. It precipitates because the water is so cold and our product of 2-butoxy-naphthalene is not soluble in that cold water. Then, once all the solid has precipitated, you will use a vacuum filtration in order to purify the crystals and get your solid result. Once you've allowed your crystals to dry in the vacuum filter for about 10 to 15 minutes, you will then weigh how much solid you did yield and do an IR spectrum with that solid. To end the experiment, you will deal with all the waste products that you made and use the non-halogenated waste container to pour your reaction mixture into. Next, we'll be assessing the purity of our product. So for our TLC plate, we have 3 distinct spots, and the S position, we can assume that is 2 naphthol, which aligns with 2 spots in our R and combined spots. So we have 2 other spots left over in the TLC plate, and we can presume that the top spot can be the 2-butoxynaphthalene and the bottom spot can be the solvent used in our reaction. While the TLC plate cannot tell us a lot directly identifying the product that we made, it can still tell us a lot about the reaction, as we only have 3 distinct spots which line up with the 3 products that we assume to be still in our reaction flask. When looking at the IR produced from the experiment, we see the peaks that we expect when looking at the molecule. We can see the carbon-oxygen bond at around 1600 and all the different carbon-carbon bonds at around 3000. When referencing this IR spectrum with database IR spectrum for 2-butoxynaphthalene, we find that the peak BMs are very, very similar, even though their strength of the peaks may not be the same. This can also lead us to a high degree of purity made from this experiment because the IR spectrums line up so well with database measures. In the organic chemistry lab, the IR spectrum is a great tool in assessing the purity of a product. In our IR experiment produced for 2-butoxynaphthalene, there are very little impurities initially present on the IR spectrum, and also when referencing to the database, they've lined up very, very similarly. This can lead us to presume a high degree of purity in our product and a very successful reaction. This reaction is an SN2 mechanism, and we know this due to many factors. The first step in the reaction is to make the nucleophile. The 2-naphthol and the NOH are added into a solution of ethanol, and the NOH works to actively deprotonate the 2-naphthol because the O- is a really good nucleophile. Next, we have the substrate of the 1-iodobutane. This is a primary alkyl halide, meaning it is very unhindered and that it will not form a carbocation intermediate. The fact that it is also added second leaves us to believe that it is SN2. Once the 1-iodobutane is added into solution, the iodine will leave because it is a good leaving group. Then the exposed carbon will be attacked by the O- nucleophile in order to make the carbon-oxygen bond that we see in the product 2-butoxynaphthalene. This is the reaction mechanism that took place in the second half of the experiment. We can see the nucleophilic attack given by this negative oxygen onto the carbon that is exposed once the iodine leaves. The iodine is a really good leaving group because of its ability to handle the electron density since it is such a large atom. Now, we can see in the transition state, this is the characteristic XN2 look. We can see the negative oxygen attacking the carbon from the back as the iodine leaves. Now, if this was an SN1 mechanism, we could see the racemic mixture of the oxygen attacking from both sides, but we do not see this since it is an SN2 mechanism. Now, our product is one isomer of the 2-butoxynaphthalene because of this attack from the back of the nucleophilic oxygen. Now, I will be giving a summary of all the purification and characterization techniques taught in the organic chemistry lab. The first technique I'm going to be covering today is recrystallization. This is known to take impurities out of a solid. The process of a recrystallization is to first choose a solvent that dissolves your solid only a little bit at low temperatures and then very well at high temperatures. After you choose your solvent, you will then dissolve all your solid into the solvent by gradually heating it up on a hot plate until just below the boiling point of the solution. You will then allow your supersaturated solution to cool gradually, possibly to below room temperature in an ice bath, and by doing this, you will hopefully form good crystals of your solid of interest and leave all the impurities behind in the solution. Most likely, you will then go on to purify your solid even more by putting it in a vacuum filter. Next is gravity filtration. Gravity filtration is useful for when you have solid impurities in your solution that you want to get rid of. The process of a gravity filtration is to first set up an Erlenmeyer flask with a stemless funnel on top and a fluted filter paper. You'll then clamp everything down and pour your solution through the filter paper, allowing your saturated solution of your compound of interest to fall into the Erlenmeyer flask, and the precipitate solid or the impure solid in your solution will be caught by the fluted filter paper. This was used back in question 2 when I separated benzoic acid from my solution of caprolactone and acetic acid. Next is vacuum filtration. The process of a vacuum filtration is to first take your solution with either precipitate solid or crystal solid and pour it through a Buchner funnel with a filter paper on it. Then, by using the power of a vacuum, it can suck all the liquid out of the crystals and hopefully dry them into a white fluffy crystal that you will use further in your experiment. This is very useful for if you are using a recrystallization and you have your precipitate solid stuck in solution. You can then go and dry those crystals in the vacuum filter to be able to get a usable product for the future. One very useful characterization technique in the organic lab is melting point. The process of figuring out a melting point of a solid is to first put it in a one-end capillary tube and put it in the melting point apparatus. Then, using the machine, you can heat up your solid slowly and look through the lens to see exactly what temperature your solid melts at. By recording those temperatures and referring them to journal data of what you think your solid possibly is, you can confirm your solid, or you can realize that your solid has impurities causing the melting point to vary. It is one useful for confirming identity and also realizing if you have impurities in your solid. Next up is the TLC plate. The TLC plate is a characterization technique that can 1. Tell us the identity of a product when compared to something in identical conditions. It can 2. Check for any impurities in your compound or solution. And 3. Measure the progress of a reaction. A TLC plate can be used to measure the purity of your compound by simply looking at how many dots show up on your TLC plate. If you're assuming that your compound is pure, it only has one substance in it, and it comes up with more than one dot, then your compound is impure. Every compound has a separate RF value based on the eluent used and the polarity of both your compound and the eluent used in the TLC. So by seeing how many dots show up on your TLC plate, that's how many compounds are present in your solution. A TLC plate can be used to determine identity because under the exact same conditions, compounds will produce the same RF values on a TLC plate. So let's say you have a reaction mixture that you want to confirm the identity of one of your products. You can then dissolve your solid product in the exact same solvent as you have for the reaction and put it on the same TLC plate. So you have a dot of your reaction mixture and then a dot of the product that you replicated in the same situation. And if they come up with the same RF value, then you can confirm the identity, along with further tests to, of course, further confirm it. But the TLC plate is a good starting point. The TLC plate can be used to measure the progress of reaction by taking TLC plates at separate points throughout your reaction. In the organic synthesis lab, if we were to take a TLC plate at half an hour, 1 hour, and 1.5 hours, we would be able to see more dots or more intensity of dots showing up throughout the reaction. In the organic lab, another purification technique we have is distillation. Now there are 3 types of distillation: simple, fractional, and steam, but we only use the simple distillation in the organic lab, so that's what I'm going to be covering today. Simple distillation is used when you have a solution with 2 liquids that vary in boiling points of 100 degrees Celsius. Now, by utilizing the fact that we have 2 very separate and very drastic boiling points, we can then boil off the lower boiled compound and, by using a condenser, collect the steam and in the liquid form in another location. This is useful for separating liquids contaminated with liquids and ending in 2 products that we can both use separately in an experiment. The graph that we get from an IR spectrometer is very useful in determining identity because we can look at the product that we're supposed to produce from the reaction and correlate different functional groups to different peaks on the graph. Also, if we look at our IR spectrometer graph and see any peaks that we weren't normally expecting from our product, we can help identify impurities present in our solution or product. A gas chromatographer works by taking advantage of the mobile and stationary phases of a gas, and by measuring the exact time that the gas was in the apparatus, it can be linked to its identity. It can also be useful in determining the concentration of the gas in the sample by giving us an area under the peak of the retention time. Another purification technique we have in the organic chemistry lab is extraction and washing. Now, I already explained this in question 1, but I'll do a quick summary again. Extraction is removing your compound of interest from an impure solution by dissolving it in a separate solvent that you add. Washing is taking out impurities from an impure solution to leave your compound of interest. An example of a washing is back in question 2 when I separated the caprolactone and the acetic acid. Now let's say my compound of interest was the acetic acid. I added the hexane to then wash the caprolactone out of the aqueous acetic acid solution. Another purification technique we have in the lab to take as much water from the solution as possible is the addition of drying agents. There are very many drying agents, as you don't want the ions of the drying agent to react with anything in your solution, but their main purpose is to get water from your solution and then make a clumped solid at the bottom of your reaction flask. Now, to remove your solution from the drying agent, you can simply decant with a glass rod from your beaker. My favorite purification technique is the rotovap. The rotovap is used by putting your solution in a reaction flask and attaching it to the rotovap apparatus. Then a vacuum is pulled in the apparatus and a condenser is turned on, which allows the boiling point of your solution to reach the absolute minimum that is possible. Then, by lowering your reaction flask into a water bath, you then slowly heat up your solution, allowing for it to boil very, very slowly. And by the end of your boiling, ideally you are left with a solid that you can extract from the reaction flask, or a very, very saturated solution, which then can be easily crystallized with other techniques. The last purification technique that we use in the organic lab is the reflux apparatus. The reflux apparatus is useful for reactions taking place over a very long period of time, because any liquid that is boiled off and turned into the gas phase then hits the condenser and turns back into a liquid. This allows for the solution to be kept at a very constant volume and to not be all boiled off and left with your solid, which would be very bad for the reaction.